talk is about error correcting codes for the Z channel and strategy for the Half-Life game. And I will start to describe, because I don't know if all familiar with this, to describe the Reni Ulam game. And I start with the game, then some parts of the history. Then I will tell you when the game is sequentially and non-sequentially. Then I come to a topic that is related to it, to data transfer with noiseless feedback. You will see that each game strategy is also a strategy for this feedback channel. I will give you the model, and I also will talk feedback versus non-feedback and the result there. Then I show you the relations. That means how we can use a solution for the game, the game tree, as a coding strategy. And then I will present some known results for the binary channel. And I go to the Curie game, because in this Curie game, together with Volodya Lebedev, we developed, and Rudolf Alswede, we developed a so-called rubber strategy, which we later use. But it's easier to understand it for the Curie game. And with this rubber method, we find the first strategy for the Z channel, but we could improve it. And the Z channel gives you also strategies for the Half-Life game. I will explain you later what it is. And finally, I will tell you something about unidirectional channels, and you will see that we can immediately apply our result for the Z channel also to this unidirectional channels. Okay, let's start with the Berlekamp Ulam Reni game, or however in which order you call these things. So it's a very easy game. So here Pinocchio is one person. He thinks of a number between here 1 and, I don't know, 23 perhaps. And we have Paul, and he have to find out which number Pinocchio have in his mind by asking questions for a subset. For example, he can ask, is X in the set 5, 6, 7, 8, 9, 15, 3? And then Pinocchio say yes or no. And of course, you all know if Pinocchio always says the truth, then you need the logarithm of the number of numbers you have for a solution just by having it in each step. That's really easy. So therefore we make this game a little bit more complicated. So we allow Pinocchio to lie a fixed number of time. So for example, he can lie 1 time or 2 times or something like this. And Paul knows these rules, and so again he have to ask questions. And the main question is now, how many questions have Paul to ask to find out the number of Pinocchio if he knows that Pinocchio is lying t times? Of course, it's a self-controlled Pinocchio, so his nose is not growing, so Paul do not see if Pinocchio says the truth or not. So there's some history. So Reni was the first who formulated this problem. So he formulated as a Bar Kochba game. So there's a story behind it, which is in one of the papers of Reni described. I think Bar Kochba is very prominent, and no one knows if the story is true, but it said that Bar Kochba was sent out as a scout in a Roman camp because he was a revolutionary against the Romans, and he was captured and tortured, and he cut out his tongue, but then he escaped, and so he cannot speak anymore. And so how they can communicate now? So, and how they communicate is that Bar Kochba, that people ask Bar Kochba questions, and he can only answer by yes and no, by nodding or shaking his head. And this is what called the Bar Kochba game. So in 1964, Berlekamp, in his PhD thesis, called some very similar game quiet question, noisy answer game. And his goal was really to to develop error correcting codes with feedback. You will see in a minute or in some minutes how it's connected. And then in 1976, Ulam formulated this problem again in his autobiography. And so this game have many names in the literature. First, after 76, a lot of people from combinatoric called it Ulam game. Then it was called Berlekamp Ulam game after they find out that Berlekamp did it earlier, and then they found out that Turini also did it. And so there exist a lot of names for this game. So how we can make a statistic of this, or how we can write it down. So for example, you can write here, let's assume Pinocchio thinks of the number from 1 to 8, and he's allowed to lie 2 times. Then in the first step of the game, he has these 8 possible numbers. So we're doing worst case analysis. And let's assume that the question by Paul is first, is a number from 1 to 4. If Pinocchio answers now yes, then Paul can do the following statistics, and he knows for the number from 1 to 4, Pinocchio is still allowed to lie 2 times, because then he said here, if he said here the truth. Now there's a possibility that he was lying here. Then the numbers from 5 to 8, Pinocchio is only allowed to lie now 1 time. That's this set here as 1. And so the game continues. Let's do the next step again. Let's assume in the next step, Paul asks, is the number 1, 2, 5, or 6? And Pinocchio says no. So he gave a positive vote for 3 and 4, and for 7 and 8. So 3 and 4 stay here, because if it was 3 and 4, Pinocchio is still allowed to lie 2 times for these numbers. If it's the number 1 and 2, you see, then he lies here. Then he's only allowed to lie 1 time. If it's the number 7 and 8, then it stays here because he's allowed to lie 1 times. But for the number 5 and 6, you see, he never says the truth. So he's not allowed to lie for 5 and 6, because then you have to lie 3 times. And Paul can go on and always make this statistic here. And at the end, at some time, he have only one set with 1 number, and then he can say, yes, I know the number. In this case, it would be the number 3. That's one way how Paul can look at the problem and how he can get a solution. You see, it's independent which number are there. It depends only on the cardinality. Therefore, I can also write these vectors. I will use them sometimes. That's here 800. That means 8 numbers where you can lie 2 times. And 44, that means 4 numbers you are allowed 2 times. And 4 numbers you are allowed to lie 1 time. And so on. And if only 1 is in the vector and all others are 0, then you know you have solved the problem. Of course, you can also draw a tree for the solution. So you can also write a game tree, for example. Here you write always the first question of Paul, and then depending on the answer of Pinocchio, let's say to the left it's no, and to the right is yes. You ask the next question, and so on, and then you know the statistic. And for example, here it's just for 3 numbers, because otherwise the game tree is too big. And then you see always you follow this line here, and you finished here, and then you know what the number is. So we have this possibility to have a game tree, and this is somehow it's a strategy of Paul how to solve the game. What I told you now, it's a sequential search problem. That means what I describe you, there's a question by Paul and an answer by Pinocchio, a question by Paul, and so on. But of course, you can also think of a non-sequential search. You can also think that Paul have to give a list to Pinocchio with all possible questions, and Pinocchio have to answer them, and then Paul have to find out the numbers. That would be the non-sequential search. And of course, you can also have something in between. You can also say, for example, we want to do it in 2 steps. That means Paul gives a list to Pinocchio. He answers his questions. And depending on this answer, he gives a new list to Pinocchio. And again, he answers the question. And then Paul have to find out the number. And again, we want to find always the minimal number of questions Paul have to ask to find out this number. These are the versions somehow of the game. Now let's come to the transmission problem. So we want to use error correcting codes with feedback. What does it mean with feedback? Sometimes if you, for example, if a satellite want to send some data to Earth, for example, from some pictures, then you have the problem that you only have a weak sender here as a satellite because it have to be small, and you have some errors here. But perhaps at Earth, you have a big station, and the station have also a very powerful sender. And let's assume he can feed back just the received bits of the satellite. And the question is now, does it improve the rate? Can we improve something if we do this? Does it make sense to loop back these things? If we can improve it, of course it does. And that's somehow what we call transmission with feedback. So more formally, we have here a sender who chooses a message M out of M possible messages. We have here, let's start with the binary coding alphabet here. So we have 0 and 1s going over the channel. And then we have noise. That means a 0 is changed to a 1 and a 1 is changed to a 0. That means the receiver always decide what he have received. And there's some feedback to the sender. That means the sender always immediately see what was received by the receiver. So if you look, then our encoding algorithm is somehow we have encoding which depend on the message and of the I-1 previous symbols. So that's for the I symbols which were received by the receiver. So that means we are when we want to send a message, then we send the first bit. It only depends on the message. Then we send the second bit, which depends on the message. And the first received bit, and so on. And for example, the last bit depends on the message and the n-1 bits received before. So, and now how we can use a game to solve these things. So let's assume we have a game tree for M messages or M numbers. So we want to send M messages. And so we look at the game with M numbers, and we know that that for some reason we know that in our system at most T errors can occur. Then it corresponds to a game tree where Pinocchio is allowed T times. Let's assume that this game tree here. How we can use this game tree to for the transmission? So we assume that the sender and the receiver have a safe game tree. The sender selects the number to be transmitted, that's the message, and answer the first question of the game tree here. And for example, he wants to transmit a 2, then here he follows the path to yes. If you want to transmit a 1, then he follows this path to no here. And for yes, he sends 1, and for no, he sends 0. And depending on the received answer, the sender selects the next question. And so on. And you see, if the game tree is a winning strategy for M messages and T errors, then we can use it for transmitting also M messages if T errors happen. Because each error in the channel now corresponds to a lie. And that means there's a direct connection to such games and also to submitting messages over the channel. And it also holds the other way around. If you have a channel strategy for the channel, then you can use it for a game tree. And sometimes it's good to have two different viewpoints. Sometimes it's easier to find a game strategy. For some strategy, it's easier to describe them as a coding strategy. What we want to do is an information theoretic analysis of this model. So we say therefore we have to define the numbers. I used them already. N is a block length, or before for the game it's the number of questions. T is the maximum number of errors or lies. And we want to look at tau over n, because you can, normally for a channel, it's reasonable to assume the more bits you send, the more errors could happen. So we assume that the errors are proportional to the block length. And so we call T over n, we call tau. That's the maximum error fraction. And we want to do a purely combinatorial analysis. And we want to look at the asymptotic case if n goes to infinity. So if the number of bits goes to infinity for fixed tau. And now we want to find the maximum amount of errors proportional to the block length. This is called the rate of a code in information theory. It's defined by the logarithm of the number of messages divided by n. You see here, if we are in the error-free case, then the rate is 1. So then we can use 2 to the n messages, and n over n is exactly 1. So the highest possible rate is 1. And our goal is now find the maximum achievable rate for channels which at most tau n errors. And this is called the capacity error function. And there's already some work on it. So we look at the binary symmetric channel. That means, you see, when I connect them, that means an error can happen from 1 to 0 and from 0 to 1. So later we will look at the Z channel. When we leave out, then we can only have an error from 1 to 0, but not an error to 0 to 1. But let us first look at the binary symmetric case where all errors are possible. And this is already solved. Let's go back. This is already solved. There we know the capacity error function. The capacity error function was mostly done by Berlekamp in his PhD thesis. So he showed that, for people who know this is somehow the Hamming bound, the Hamming bound for feedback, or sphere packing bound with feedback here. It goes, if you follow the line, it goes here to 1 over 2. And this is, of course, an upper bound. This was shown by Berlekamp. And then you have this tangent here to the sphere packing bound, starting from 1 over 3. And this tangent was shown by Berlekamp also to be an upper bound. So, and then he can give also a strategy that reach this tangent here. So he showed that this is an upper bound, and he could show that the upper bound is tied in this region here. Then you have problems for the rest of the part, the sphere packing bound. What he can do, he find infinitely many points here on this line, but he cannot show that it can be completely reached. That was done by Zigangierov. He showed that also this part of the bound is also tied. He finds a strategy for this, and therefore we know for a channel with feedback, or for this game, if you do an information theoretical analysis, then we know that is the best possible rate. So that's the capacity error function. The situation is different if we look at the case without feedback. When we look at the case without feedback, that's an open problem, and it's open long times now. So there we know that we have here this Gilbert-Wassermorf bound, which is a lower bound here, that this bound here, and we have the linear programming bound here, which is the best known upper bound. But you see here's a gap. So here no one knows what happened in it. So it's still an open problem to solve, to calculate the capacity error function for this channel without feedback. And you see it's not so good. So in many books you must be carefully. Many times they don't write here down the number of errors divided by n. In many books you find here the distance divided by n. Then this curve goes until 0.5 instead of 0.25. So because the distance is 2 times the number of errors, so then the picture looks a little bit different. But to make it comparable to the case with feedback, I think it's it's better to look at the number of errors divided over n. So what of course we can also do is to divide the set into Q partitions. So to look at the Curie case, if you have a Curie alphabet, and then we look at the rate to the basis Q. Some people already also use here the basis 2 and say we look at the bit rate. But we do here the capacity Q. The only thing what you get is a factor there because you have to change the basis of the logarithm. So I like to do it with when we write here the number of symbols here, because then you always have that the best possible rate is 1. And in this case, some time ago, now already 15 years ago, together with Alswede and Lebedev, we got a result for this channel. So we get a very similar result like Berlekamp. So if you here look at the blue line here, then we show that this blue line is an upper bound. It's a sphere packing bound until 1 point here. And we have a tangent now, instead of 1/3, we have a tangent here from 1/2. Which is a tangent to the sphere packing bound again. And we could show that this is an upper bound, and like Berlekamp, we could show that this is also a lower bound here. So, and we can find, again, like Berlekamp, many tangents and many points here, but no one could show until now. I know that some people worked on it, that this part of the bound is also tight. So this is a nice open problem. Try to solve it, and that would be very nice if someone could solve this problem. Why I am presenting this problem? Because it was to reach this bound here. It was a very simple strategy what we developed. We call it the rubber strategy. So the idea is just to, if you have Q symbols, just to use the 0 as a rubber. So we encode somehow only, we use for code words only the symbols from 1 to Q-1 and the 0 as a rubber. So it goes as follows. So let's assume, so we give each message encoding. Here I did it for 3-array coding alphabet. So we have the symbols 0, 1, and 2. So we have for the sequence 1, 2, 1, 1, 2, which corresponds to a message, and we want to transmit this message to the receiver. So let's start. We first transmit a 1, the receiver receives a 1, and then we transmit a 2, and the receiver receives a 1. That means an error occurs. And our idea is just to use the 0 now as a rubber symbol. That means we send a 0, and the 0 stands as a rubber for the receiver. So let's assume, to make it not too complicated, that the 0 is received correctly. Then he erased the first the 1 and the 0, and we continue to sending a 2. So then the receiver maps this 1, 1, 0, 2 to 1, 2. And we continue in this way. And this strategy works. You have to be a little bit careful, because sometimes also the rubber can be destroyed, and there could be an error, but that's also no problem. You always can correct it. And you send again a 0, and it erases the previous symbol and so on. And because you have only a finite number of errors, this always works, and it's always also asymptotic optimal. So it's a very nice strategy to receive, to show that this part here is optimal. And what is also very nice, which we find out later, that we can also use this strategy for other tangents. So instead of 1 0, we can use 2 zeros and as in rubber. So it means if the receiver receives two zeros, then this is a rubber for him, and he erased the symbol before, and we continue the transmission. That means then you can map all your messages also to sequences which contain at most 1 0, and then we get this tangent here to this thing. And it turns out that also for the binary case, we can find a new proof for Berlekamp strategy. So Berlekamp gives a totally different strategy, but we can show if you just use with 1 0, it's impossible to do anything for the binary case. But with 2 zeros, it's possible. And we receive really the Berlekamp tangent from 1/3 for the binary case. So we get a new proof for the binary case. So Berlekamp, what did I write here? And for our new algorithm, we assume that for the first, okay, sorry. Now I come to the case that we want to use less feedback. So always people say, oh, feedback is very expensive. We send all feedback, always each symbol. It's very different and it's very expensive. And therefore we were looking at strategies where we use less symbols. And our idea was the following. We first send K symbols and then we do a feedback code. And we will show that we can also achieve the Berlekamp bound in the binary case, and for the query case, we can also attain our bound. And the idea is in principle very simple. At the first case position, we transmit information symbols. That we again means we map each sequence to its binary or ternary, each message to its binary or ternary sequence, and send this symbols over the channel. And then after this, we see where the errors happened. And then we have to tell the receiver how many errors happened and at which positions they happened. It depends. And if you only look at the binary case, we only have to say how many. We only have to send him the position. The other case, we also have to say him what error happened. And this message really works. So I will, if you are interested, you can read our paper. But this message is really working. That means we can really do it in this case. First send K information symbols, then use the two rubber method to send to transmit where the errors happened. And then we get as a theorem here that we get this rate here. And it's very interesting that and that's exactly the lower Berlekamp bound, and so it's also optimal. So we can save some feedback also. Of course, now you can look at general channels. For example, you can look at channels where only some error can happen. For example, here you see that's just an example. Zero can only there can only happen that 0 goes by error to 1, but it's not possible that 0 goes by 2 to an error. Or 0 goes to 3 or something else. So only with some errors can happen. And how we can analyze this information theoretically. Therefore, we look at the first special case. We look at the Z channel. And for the Z channel without feedback, Berlekamp already shows that it has the same capacity error function than the binary symmetric channel. So we know here in this case for without feedback we have the same capacity error function, and it's still open. You get the same picture as for the full channel here. That was shown by Basaligo. Now we will look at this channel with feedback. So is there a similar theorem with feedback? So is it perhaps also so that we can say we know the capacity error function with feedback for the full channel? Is there a similar thing for feedback? No, because we can improve this very easy with the rubber strategy. That was why I presented this to you. So the solution is now only one error is possible from 1 to 0. And now if the receiver receives 1 0 0, he can immediately correct it to 0. Because it's not possible that the 0 goes to, so if you look here at the channel, so it's only possible a 1 goes to 0, but it's not possible that a 0 goes to 1. That means if I send a 0 here, then I know the sender really sends a 0. So it's not possible that here something other happened. It's not possible that we have to erase the 1 and replace by 0 or something like this. That means we need one symbol less than we need for the strategy when we have the full channel. That means we get here, that is the first result, 1 minus 2 tau instead of 3 tau. R0 is still the same here. So we can improve it. That means we have now a line starting from 1 over 2. There we get a positive rate. So we are much better than the full channel, where we know after 1 over 3, the capacity error function is 0. The question is now, first we thought this is perhaps optimal and we try to find even an upper bound for it. But then, together with Nikita Polyansky, we find out that it's even possible to get better rates. So I will present you now a strategy where it's possible that for every tau, we have a positive rate. Only if tau is equal 1, we have the capacity error function 0. And how does it look like? What is the idea of this strategy? So M will be the total number of messages, and N again the number of channel users. And tau again be the fraction of errors. Now we select a W. This is a weight parameter. And we define our first N1. So you will see we divided, we will send again in rounds. So the first round we send N1 bits. And now we have to define how much bits we send in the first round. So N1 is now defined in such a way that M is equal to N1 choose W times N1. So that means N1 is approximately log M over the entropy of W. Now, what does Alice do? So here I call now the sender Alice, not longer Pinocchio. Sorry for this. Alice wishes now to send a message M, and she can encode it to a binary string of length N1. And we will do it. We will do it with WN1 ones. So we encode it only to sequences which have WN1 ones. And so it also have 1 minus WN1 zeros. So because we are in the binary case. And so at the first N1 channel users, she sends the strings at once. Now, because we have this fixed number of ones, and the receiver knows it, he knows how much errors happen. So let T1 denote the number of errors for N1 transmissions, and thus the number of received ones is WN1 minus T1. And from the view of Bob, now, when he looked at the message he received, he knows how many errors happened, and he can reduce the number of messages now, because it's not possible that all possible messages are now happens because he received a code word, and so now we reduce the number of messages to 1 minus W times N1 plus T1 choose T1 messages. And only these messages are consistent with the output, so with the received sequence. And so we can now define N2 as this, and we continue this in the same way like before. Now, Alice also knows how many messages are possible, and so she maps these messages to this number here, and again sends this N2 with this weight here. So let's look at the procedure again. So Alice wants to send the message M. It's somewhere here. She encodes the message by a string of length N1 with weight WN1. And suppose now T1 errors occur. So from Bob's perspective, from the receiver, so there are only M2 messages which are consistent with the first output from, this is Y1 to YN minus 1. To YN1. And now she continue in this way. So here's a picture. So for every I, you see, for every I we can do this and continue and iterate this procedure. And our goal is we want to iterate as long as only one message is left. So you see, we did it here. First we sent N1 positions, then we reduce the number of messages, then we send N2 positions, we reduce the number of messages, and so on. So we must be a little bit careful. You will see for the last steps, we cannot use this strategy, but in principle, this is the idea of the strategy we use. When we are analyze now the strategy, we have to calculate how big is our N until we are left with only one message. So we have to sum up. We know how big is Mi, and we know how big is Ni plus 1, and we have to sum up this. And then we can, with this, we can get a lower bound on the rate. So we have here, I determined here the problem here. Using Salem flow doesn't work good when the number of remaining messages is small. And there we switch to another strategy. So for example, we can use, we call it the rate strategy. If we have only a small number of messages, perhaps we order them to the rate of, if we only have n messages and n bits are left, then if we want to send message 1, then we send the code word 1 and all zeros, message 2, 1, 1 and all zeros, message 3, 1, 1, 1 and all zeros. So very simple strategies work there. It's just to be, one have to be a little bit more careful in the analysis. So if you look now at the rate which we receive here and look at the picture here, you see what I already told you. The rate goes here until 1. So already, if you are very small, you can go with positive rate. You can send messages, and if you compare it without feedback, as you remember, for the Z channel, the best known thing is the Gilbert-Wassermann bound, and it goes to 0.25 here. So there's a big gap now, and for some reason. If you look now also as the strategy with the rubber, which I described you, this is a tangent to our bound. So you see, that's our old idea with the rubber, where we go to 0.5, and somehow this is such a nice curve here. So what we conjecture is somehow that this is also optimal. We are not sure about this, but it's an entropy formula. If you look at this is a very nice formula here. It's this one here, and it looks very nice. And our conjecture is somehow that this is also optimal. Unfortunately, we were only able to get in our paper. We get a upper bound, but this upper bound is not so good. If you see here, it's far away from our lower bound. But somehow our conjecture is that this lower bound is also optimal. And also this is again an open problem where perhaps you can work on it if you're interested. And also if you look in our, so we also got a problem. This problem is also related to unidirectional channels. So unidirectional channels, this is a case if you have two binary channels, the Z channel and this channel here, where the Z is here in a wrong direction. That's called the inverse Z channel. So, and if you start sending over the channel, you do not which of these channels is realized. But during your whole transmission, only one of this channel is realized. And therefore, you can use for the capacity error function, it doesn't matter if you look at the Z channel or at this unidirectional channel. That means our result also gives a lower bound and an upper bound for the capacity error function for unidirectional errors. So this was a question Han Fink asked us. How is it related to unidirectional channels? And it's not difficult to see that we get immediately with this strategy for the Z channel, also a strategy for the unidirectional channel. We also have a paper about this. In this paper, we calculate this. It's a little bit older paper. I think it's 2 years ago, together with Volodya Lebedev. It's a joint paper. So we we showed this and showed that this is also valid for the unidirectional channel, but now with our new results, we can improve immediately this result. Yes. Okay, so I want to thank my co-authors for this paper, so Volodya Lebedev, so many of his results I cited today, and also a lot of open problems. Perhaps someone is interested of you. I think most of our papers are also on archive. I was not sure. I think at the moment it's not the actual version, unfortunately, of our paper as on archive. We have to update it. I think I have to do this. I forgot to do this. There's the old version. It gives you still the idea of the algorithm that's in there, but we improve the upper bound a little bit. And in the new paper, we also do a complexity analysis. And there's also the paper together with Volodya and with Georg about this unidirectional channels, where we only use the rubber strategy to get a capacity for this. But if you read this paper, you will immediately realize, together with this result, we can improve this result. And then, of course, there's a paper together with Volodya and with Rudolf Alswede about the Curie channel, where we also have this conjecture, which I present to you. This conjecture is open now for 15 years, and I would be happy if someone can solve this. So, okay. Yes, here you see already all the things I talked about. This is a general paper. It's somehow an overview together with Volodya and Georg. It's called How to Apply the Rubber Method for a lot of channels. So there we describe how it's possible to modify the rubber method and for which kind of channel we can use this. Then here, that's the paper about the Z channel. I hope I will update it, and then you can find also the actual version. If you want, I can also send it to you. So just write me an email. And this is the paper which already appeared in this year. It's about unidirectional channels. So the bounds can be updated with this result, of course. And here about the result, I told you about partial feedback. It also appears this year in Discrete Applied Mathematics. And about the story and all possible results, there's a very nice book of Ferdinando, who also is, I have a lot of papers also with him. When I was in Bielefeld, he was also 5 years in Bielefeld, and he wrote a nice book about fault-tolerant search algorithms, which is where you find a lot of results in this direction, and I think all results, all older results I present to you today. Yes, okay. Thank you for listening, and if you have questions, please ask them and find out if I'm telling the truth.